Welcome again. It is a connected topic. In fact, in a sense the topic should somehow come before crystal, because how do you know, how did mankind come to know that there are 7 crystal systems, 14 Bravell lattices, or copper is FCC, or C60 is also FCC, and so on. So, that experimental technique which establishes crystallography is X-ray diffraction. In fact, it was such a successful experimental technique for crystallography that initially the crystallography itself was given the adjective X-ray, and people had books or people had courses, X-ray crystallography, the crystallography or crystal structure as determined by X-ray. Because the experimental technique, the basic experimental technique, of course, there are other diffraction, neutron diffraction, electron diffraction and so on, but the basic technique for crystallography is X-ray diffraction. So, it is very, very interesting. The history is even more interesting. This is a book, Landmark Experiment in 20th Century Physics, and let us look at the content. The first one is wave nature of X-rays, and the wave nature of X-rays was established by X-ray diffraction. So, Lave's experiment was considered to be one of the greatest experiment in physics. Any list of great experiments of 20th century, in this list it was number 1. In all lists it may not be number 1, but somewhere it will appear in the top 10 or top 20 experiments which were performed in. Very automatic ho gaya kya? So, now look at this this shape, the snowflake, beautiful snowflake, nice 6-fold symmetry, but not man made, made by nature. So, this intrigued people, and that was the beginning of crystallography, that why people asked, why crystals, why natural crystals, why snowflake falling from the heaven is having such nice regular external shape. And this was a very fundamental question of science in 1600s and 1700s, very, very fundamental question. Attracted greatest of mind. On the top there is Kepler of the astronomy fame. So, we think that Kepler only studied heavenly bodies. No, he also studied things at the ground level, the structure of crystal, one of the first person to postulate on why crystals have regular external shape. Robert Hooke, Hooke's law. In fact, Hooke is father of microscopy. All metallurgists in the morning should show agarbatti to Robert Hooke. His book Micrographia, was the origin of microscopical study of materials. For the first time, he used a microscope to study all kinds of material. He also studied crystals, and his question, for him also this question came, why crystals have regular external shape. And they started guessing microstructure property relation. So, they started guessing. Atoms were not even fashionable words those days, but they started guessing that there must be something inside. The inside parts are also there, and those parts must be regularly arranged to give you the nice external shape. So, this was their postulate, which in 1750s or so they proposed, but after that there was, but what are these parts itself was not defined, atom was not defined, and how to look at those parts, whether they are regularly arranged or not, was also, there were no tools. So, this question in 1750 means it remained as a hypothesis. The tool came much later. The tool came much later in 1895 when Röntgen discovered X-rays and got the first Nobel Prize in physics, 1901. That was also an accidental discovery, and it is a nice story. You can look up Google how he came to discover. And it started getting used, and this is the first use of X-ray picture. Of course, what will it be? It will be hand of Röntgen's wife. So, he X-rayed that. Of course, probably gave heavy doses and all, nobody knows, because its medical danger and all were not established at that time. So, he expressed his love for his wife by using the latest Nobel Prize discovery to create the first image, X-ray image. Now, so as soon as X-ray was discovered, medical uses and all started. But then one question which was unsolved, are X-rays waves or particles? Huge, big question. Early 20th century, if you see 1895 was the discovery. Early 20th century, 1900, 1905, 1910, enormous number of papers and all sorts of speculations. No, it is particle, no, it is wave, no, it is a longitudinal wave like sound, no, it is a transverse wave like light, and so on. So, it was a big question. In fact, the name itself was the question. It was given the name X-rays because people did not know what it is. So, the unknown is X in our algebra, every kid knows. So, X-rays. Then came this, what is ranked as one of the greatest experiment of 20th century, the Lave's postulate. He used two ifs. If crystals are periodic arrangement of atoms, and if X-rays are waves, then crystals should act as 3D diffraction grating for X-rays. Diffraction grating for light was a well established thing. There were 2D diffraction grating, periodic arranged lines, and light gave you sharp diffracted beams. So, based on that, he generalized that when you have a 2D diffraction grating, you have a 2D diffraction pattern, then if people are thinking, people are saying that external shape, and nobody had thought till then, till X-ray came, nobody thought that copper is a crystal or something. Well, there were speculations, but it was not established fact. Crystal meant something like snowflake or other naturally grown crystal, gemstones and so on, which has nice external shape. So, this was just a postulate, that external shape, Kepler's postulate or Hooke's postulate. So, if crystals are periodic arrangement of atoms and if X-rays are waves, then it is a big two ifs and big then, crystals would act as 3D diffraction grating. Only way to check this will be experiment. Nature can be kind or nature can be unkind. Nature was very kind to Lave, that he did get a diffraction. If diffraction was not there, then neither of these questions was answered. If diffraction was there, both the question got answered in positive, because if you do not have a diffraction, maybe X-rays are wave, but diffraction is not there because crystals are not periodic, or you do not get diffraction, crystals are periodic, but X-rays are not waves, and in those days particle diffracting, electron diffraction and all were not established. So, only wave like thing could diffract. So, he would have got nothing, but he was lucky with such a bad diffraction pattern, you can see, but still they could see that apart from the central beam, there are beams which are going away from the center, and that was the basic definition of diffraction, that if there was no diffraction, only the central blotch should have come, nothing else. Of course, with more modern techniques, you can see a much nicer diffraction pattern. This is a Lave technique. So, the X-ray beam is coming here. You can imagine that X-ray beam is coming here. Ashish will teach you more about this. And the crystal is somewhere here. X-ray is coming along the laser direction. Then, if the crystal was doing nothing and only transmission, then only a transmitted blotch should have been there, transmitted spot. But then, after interacting with the crystal, beams are going in different direction and being recorded on a photographic film, which is coinciding with the plane of the screen here. So, this is what is the Lave's technique, and beautiful diffraction pattern like this can be found. So, once you get the success of this experiment, and that is why it is called the greatest science, because two of the greatest questions, not one but two great questions were answered in positive, that X-rays are waves and crystals are periodic arrangement of atoms. This started the modern crystallography or which I call X-ray crystallography. Lot of crystallography means that is also genius, that without the X-ray tool, this 32 point groups and 230 space groups which I told you is not a result of X-ray crystallography. That is mathematical abstract crystallography, how many ways points can be arranged in space, and looking at the natural crystal, how many different forms they are making, classifying them and all that. That is why point groups were not called point groups, but crystal classes. In the morning class I told you 32 crystal classes, because they were classifying the crystal according to the shapes, according to the external shape. That itself they told them that there are 32 possibilities, but X-ray finally established all those things from the internal arrangement and changed to a major shift in the definition of a crystal, that crystal is not something which has nice regular external shape, but crystal is something which has nice periodic arrangement of atoms, a definition which we now use, which I gave in the morning class. Now, you saw the example of diffraction pattern. There are peaks at certain location and there are peak intensities. So, essentially X-ray diffraction analysis is analysis of peak position and peak intensities. And interestingly, I told you in the morning class we had a lot of discussion on crystal and lattice, that crystal is equal to lattice plus motif. That equation and this equation are in exact correspondence. So, if you put it now, crystal is equal to lattice plus motif, and the X-ray diffraction peak positions tell you what the lattice is, and X-ray diffraction peak intensities tell you what the motifs are. So, the peak positions is governed by lattice, peak intensities are governed by motif. So, we will look at these as we go. Now, as I told you in the X-ray diffraction example, that there is an incident beam. If nothing was happening and only some absorption of this X-ray and some transmission, then we would have said that there is no diffraction, just transmission. So, the very fact that you get a beam in a direction not expected in the direction of the transmitted beam, but in some other direction, that is what we are calling the diffracted beam. Of course, there can be more than one direction for a given sample and a given incident beam. These are different experimental techniques which use them. Now, let us look at the X-ray diffraction little bit more in more detail. So, you have a periodic set of atoms in the crystal and X-ray is coming and hitting, and of course, X-ray is not picking and choosing one particular atom, it is hitting all the atoms. But let us focus on one atom, and as the X-ray is coming, it will interact, the electrons in the atom will interact here with the X-ray and will generate new X-ray beams traveling in all directions, not in any given diffracted beam direction. So, for a single atom or for a single electron, there is no concept of a diffracted beam. Diffraction is there in entire 3D space for one atom. Similarly, all the atoms receive this X-ray. I have not shown this line for all the atoms, but I am seeing the scattered line for all the atoms they are receiving and they are scattering. Then you can pick and choose a certain direction, the blue direction here, okay, and see whether the X-ray coming from this atom 1 and this atom 2 in the blue direction, they are reinforcing or not. So, you can apply the path difference, the phase difference rule and see whether you get addition or you get cancellation. If you have an addition, then you have a strong. So, now by this longer arrow, I am saying that all these waves get added up to give you a strong. They could have cancelled also, that depends upon the phase difference, you know. So, if they are in phase, they will add, if they are out of phase, they will subtract and so on. So, if they were all in phase, you will get a strong beam, and that is what we will then call the diffracted beam. Now, now comes the Bragg's genius. This much was just a diffraction. This much what Lave also saw and got his Nobel Prize. So, Bragg had to do something new to get his Nobel Prize. So, Bragg introduced this plane. He said that for this diffracted beam, I can draw this blue plane and think of it as a reflection, that the black incoming X-ray is reflected into this blue X-ray by these mirror planes. Totally hypothetical and nothing to do with the physics here. Physics has already been done. Physics has been done that you have added all these waves and you have got a diffracted beam. Analyze it. Lave did that. Lave's analysis did not require any introduction of mirror planes, simply addition of all the waves from all the atoms, and you will predict the correct diffracted beam. But then introducing this mirror plane by the Bragg brought in enormous simplicity of the analysis of diffraction pattern, and that is why Bragg got Nobel Prize. So, of course, the beam may not be adding up only in this blue direction. Suppose this red, because each atom is giving beams in all the direction. So, it may happen that in some other red direction also the beams add up and are in phase, but then that is not appearing to be a mirror reflected from the blue. Do not worry, Bragg said. Consider now, switch off the blue plane, consider new red planes from which it will appear to be reflected. So, this was Bragg's genius. This was the imaginative jump which did not come from a logical deduction or something, but by looking at the problem and coming up with this nice mirror planes. So, what Bragg said and what is a real Bragg's law? Ask any student, Bragg law is equal to lambda is equal to 2d sin theta. No, that is trivial. That is not what got Nobel Prize to Bragg. Nobel Prize part of the Bragg's law is usually hidden in the textbooks. बोलते ही नहीं कि ये ज़्यादा important है. That for every diffracted beam, what I showed you in the previous slide, for every diffracted beam, there exists a set of crystal lattice planes such that the diffracted beam appears to be specularly reflected like mirror-like reflected from this set of planes. This is the real part of the Bragg's law. This is Bragg's genius. This is the Nobel Prize of Bragg. So, Bragg's recipe for Nobel Prize was, how did he get Nobel Prize? By calling diffraction a reflection. नाम बदल दो तो Nobel Prize मिल जाएगा. And this is his statement. This is his quote. So, he didn't discover. Why did Bragg got Nobel Prize? He didn't discover X-ray. Rontin discovered, he got the Nobel Prize. He didn't discover X-ray diffraction. Lave did, he got the Nobel Prize. Bragg got the Nobel Prize for calling diffraction a reflection. The important thing in science is not so much to obtain new facts. He didn't obtain new facts. Diffraction was already existing. Or as to discover new ways of thinking about them. He thought of diffraction in a new way, looking at it as a reflection from crystal lattice plane. That changed the whole world. That what Lave had already demonstrated diffraction, already had calculated the physics of it, would have been very, very difficult to implement for solution of crystal structure. This way of looking made it simple to solve the crystal structure. That is why Lave, although was discoverer of diffraction, did not solve even a single crystal structure, and Bragg started solving the crystal structures one after another. So, X-ray diffraction as a tool for crystal structure solution was established by Bragg, and that is what his credit is. In fact, Lave, in the very first paper on the diffraction, in the analysis of the diffraction pattern, he mixed up and he got the crystal structure wrong. Okay. So, he could not solve because of his complicated way of looking at it. He could not solve the crystal structure which actually got him the Nobel Prize. He got it wrong. Later on, of course, it was corrected. Being wrong is not that bad. But what brag? Brag is not one brag, but a Joda brag. So it's Braggs. William Lawrence Bragg and William Henry Bragg, father and son team. No need to say who is father and who is son. You can see from the picture ages. So father son, this is till now in the history of Nobel Prize, in all subjects taken together, this is the only Nobel Prize given to is shared by father and son. Shared by father. There are other father son teams which have got Nobel, father and son have got Nobel Prize, but they got separate Nobel Prize. Here they worked on the same thing and got the same Nobel Prize. This was not always good, that it is such a nice happy family. It created tension in the family because of the credit. So people will often think the Bragg's law is Lawrence Bragg, Beta Bragg's law. The full name of Bragg's law is Beta Bragg's law. But in those days, when this was not established, Bragg was just an undergraduate student at Cambridge at that time. Father was a well established professor in physics. So people will say, काम तो इसने ही किया होगा, credit मिल रहा है बेटे को आगे बढ़ाने के लिए. So many times the credit, although means actual discoverer of the Bragg's law was him, they shared the Nobel Prize for jointly solving many crystal structures together. So that was their joint work. So 1915. In 1913, 2 years back, there was a celebration by International Union of Crystallography. They declared 2013 to the celebrating crystallography year, Bragg centenary. A lot of special events were created. So this was the Bragg's first part and was the important part, that the diffracted beam appears to be specularly reflected from a set of crystal lattice plane. Part 2 is very simple diffraction calculation or addition of wave, which is done in all text. That once you accept that the diffracted beam is a reflection from the plane, what will be the relation of the wavelength and theta and the d spacing. So that is the second part of the Bragg's law, which can be written as n lambda is equal to 2d sin theta. And as I told you, unfortunately, the first part is undervalued, means not emphasized so much as the second part, which is given as Bragg's law. Second part is immediate, automatic, if you accept the first part. First part is not immediate, not automatic, has no derivation, it has imagination. So once you accept that, you can, this path difference is PQR, PQ and QR both are d sin theta. So total is 2d sin theta. 2d sin theta is equal to, for constructive interference, integer multiple of wavelength. This we know from interference physics. Now another thing which creates some problem with application of Bragg's law in problems and in crystal structure solution is this. Sometimes it is written as n lambda is equal to 2d sin theta. I am calling it the first form. Then I am changing it, take n to the other side. So lambda is equal to 2d HKL sin theta. Now if you use the d HKL formula, I am assuming a cubic crystal, but it is true for all crystals, that if you find the d for NH, NK, and d is the lattice spacing, plane spacing. So if you take d 2 2 2, it will come out to be d 1 1 1 by 2. This is always true. So in cubic crystal, for example, in cubic crystal, d is a by h square plus k square plus l square square root. Let me call it d HKL. So if I have d 1 1 1, it is A by root 3, and if I have D222, you can show that it will exactly come out to be D111 by, and if it is D333, it will be D111 by 3. Using this relationship, one can then write dHKL by n as d NH_NKNL and write lambda is equal to 2d sin theta. N has disappeared. This disappearance of n causes enormous problem to beginning students. Despite teaching all this, some of the slides are directly from my class in IIT Delhi. So, despite teaching all this, when you ask the question in the exam, they start with n lambda is equal to 2d sin theta and then get mixed up how to find n, sometimes assume something, sometimes calculate it in some arbitrary way, but nothing is required. The final useful form of Bragg's law is lambda is equal to 2d sin theta, where n is not there. But you should know that n is in a way there, but is absorbed in D. So, this is the second form. Essentially what we are saying, see, essentially what we are saying that crystal is there, incoming beam was there, incident beam, and you got a diffracted beam. And we want to name that diffracted beam. We want to name that diffracted beam. And Bragg showed that you can find a plane from which it is appearing to be reflected. So, name it according to the plane from which it is reflected. So, I will say this diffracted beam is the HKL beam, means it is reflected from the HKL plane. However, there is this arbitrariness that you can the path difference between these two could have been 1 lambda, then I will call it a first order diffracted beam. But path difference between, so if this is 1 lambda, some other beam the path difference will be 2 lambda. So, you have nth order reflection from HKL plane. Depending on this n, you define the order of the diffraction or order of reflection. Here n is always 1. So, this is always the first order. So, first order reflection, here you will say first order reflection, but you change the plane. So, if you have a second order reflection from 111, that will be the first interpretation. Instead of calling that, we will say this is the first order from 222, and we will get by that. So, it is just a language, there is no physics involved in this. There is just this algebra, little bit of algebra, that you bring this n here and call dHKL, d NH_NKNL, and what was appearing to be the nth order, you call it the first order. But can we not decide whether it is nth order or the first order? No, because the experimental tool which is available to us is this lambda and is this theta. So, we see beam is coming in which direction. So, I know the theta, and whether I assume nth order reflection from HKL plane or first order reflection from NH_NKNL plane, I will get the same theta. So, this particular beam, the theta beam, which is the physical thing, can be given either this name or that name. Physicists sometimes choose this and confuse more people in their books, but crystallographers, you will find those X-ray crystallographers who are actually into the solving crystal structure will never try to use n lambda, they will use this form, all reflections listed as first order. Now, to get the X-ray, first you have to generate it for X-ray diffraction. The way to generate it is that you impinge high energy electrons onto a target metal. So, when high energy electrons impinge a target metal, they give you X-rays of different wavelengths. This is what happens in the so-called X-ray tube of the part of your experiment. So, every X-ray diffractometer will come with an X-ray tube, X-ray generator, and in that tube the target will be one of these metals. Copper is quite common. So, if copper is there, then the wavelength which you will get out of it is 1.54 angstrom. So, these are called the characteristic wavelength. Then depending on, see, lambda is equal to 2d sin theta. So, your experiments can involve either variation of lambda, d you can't do anything, d is fixed because that is defined by the crystal, that is the crystal which you are studying. So, d is not experimentalist variable, but d is the given crystal. So, experimentalist can play with lambda, experimentalist can play with theta. So, based on this, different kinds of experimental setups have been defined. So, Lave method which I showed you, in that the lambda is variable. So, they use white radiation, mixed wavelength, not characteristic wavelength. So, variable lambda, but theta is fixed, that is the Lave's method. In rotating crystal method, lambda is fixed, theta is variable. Powder method, which is the most common and which is what I will discuss in more detail in the remaining part of the lecture, also has fixed lambda and variable theta. But the way they vary theta in the rotating crystal method, they actually rotate the crystal to vary theta. In powder method, nothing is rotating, simply because you have a polycrystalline powder, each grain is differently oriented. So, that is what is giving you a variable theta. So, millions of powder particles are there, they are randomly oriented in a space. So, X-ray will come and hit them at different angles. So, theta becomes variable. So, this is in the rotation crystal method, there is a fixed axis of rotation. There is only one axis about which the crystal is rotated in the rotation method, but in powder method it is rotated about all possible. So, in rotating crystal method only one fixed variable theta, but about one axis. Here variable theta about all possible axes. Let us look at little bit schematic detail of the powder diffractometry. So, you have an incident beam, you have a sample, you have a transmitted beam, and you will have one or more diffracted beam 1, diffracted beam 2. You have to catch these diffracted beam to get your diffraction pattern. To catch that, there is an X-ray detector. An X-ray detector moves in a circle around the sample. Sample is at the center of the circle and X-ray detector will move. By Bragg's law, you know that angle between transmitted beam and the diffracted beam is always 2 theta. Okay. This is very simple, and this is the reason why intensity is plotted against 2 theta. Sometimes students are not able to answer this question, that why are you plotting intensity against 2 theta? You could have always divided. You will not see in any other graphs that the x variable is multiplied by 2. Makes no sense. Instead of y as a function of x, you are plotting y as a function of 2x. But in this case, it makes a sense because according to Bragg's law, since it is a reflection, the incoming theta and outgoing theta is same from the plane. But you are not seeing the plane. Plane is not there for experimenter to see. So, you can't measure by any goniometer or something that here is the plane and here is my theta. So, experimentalist can't see the plane, that is why this 2 theta concept came. Experimentalist can see where is the transmitted beam going. There is the transmitted beam, he can catch that, and he can catch the diffracted beam, and then by geometry the angle between transmitted and diffracted beam becomes 2 theta, and that is why you plot intensity as a function of 2 theta. So, as the detector is moving, it is catching the beam. So, how much the detector has moved gives you 2 theta, and how much intensity it is catching gives you I. So, that gives you the diffraction pattern intensity versus 2 theta, which you get from these diffractometers. So, actual diffractometer. So, this is the circle on which detector is moving. Here is the detector. The sample stage is here inside. So, in the center of this circle, this is the X-ray generation tube. So, there will be metal target here, on which the electrons generated here somewhere there in the bottom will come up, hit it, X-ray will be produced and will be taken into this diffractometer. So, that incoming diffracted beam will be there, and then using the detector at different angles, you will catch the diffracted beam at different angles. We will get something like this, not a very good pattern.
Where we will sense the reflected beam in this diffractometer?
In that, here?
In the same detector. In the same detector,
detector is detecting only the reflected beam.
Deflected or reflected?
Nobel Prize of Bragg.
Transmitted deflected.
No, transmitted is fixed by the geometry. In fact, you will never try to actually take your detector to the transmission line, because the transmitted beam is very strong and your detector will burn. So, the X-ray diffractometer suppliers set the goniometer. So, this is your sample, this is your X-ray source, this is the transmitted beam, but transmitted beam is extremely strong. In fact, most of the energy is there in the transmitted beam, and detector is not designed for that, and the diffracted beam are extremely weak. So, detector is designed for this. So, before supplying the instrument to you, they calibrate. Without this transmitted beam, they know that this is set this to be 0. So, that when the diffractometer is here, the detector is there, you know this angle, which becomes 2 theta. So, will be labeled as 30 degree. So, on your computer output, in olden days actually one used to see this 30 degree and all on the goniometer, but now on the computer output you will get 30 degree. Okay. But it is not that you will first set the 0 by bringing the detector. In fact, most modern diffractometer will not allow, for safety reason, to save your detector, to bring it to the transmitted. In the olden days, this safety was not there, and sometimes if the student actually bring it down to 0, detector fuk gaya. Okay. So, this kind of means you will get at different 2 theta, you will get different intensities. Intensity has been, now each peak is being labeled 111, 200, 220. This is where they are identifying that from which plane this is appearing to be reflected, from which plane this is appearing to be reflected. This is what is called indexing of the diffraction pattern. So, when you have done indexing, actually you have solved the structure in a way. So, indexing is a very important part. Now, something called systematic absences, very important part of X-ray diffraction. Let us look at the BCC crystal. By our definition of D, if you find 100, D 100 is equal to A. So, A is the cube edge length. So, D 100 becomes cube edge length. Now, I say 100 reflection from BCC crystal or any cubic crystal 100. Please, for this course, for this class, reflection and diffraction, the same thing, thanks to Bragg and his Nobel Prize. So, I may write reflection or I may write diffraction, but it is always the diffracted beam, which is being called reflection after the discovery of Bragg's law. So, 100 reflection means that the diffracted beam is reflected from 100 plane. So, which means lambda is equal to 2d 100 sin theta 100, but d10 is nothing but a, 2a sin theta 100, which means planes is now what have we called, what is the n? N is 1, which means, and what was this? This was the path difference. So, when I say that 100 reflection, I mean to say that planes which have the spacing a, that is the top plane and the bottom plane, planes which have a spacing a have a path difference, waves reflected from those planes have a path difference 1 lambda. That is the meaning of 100 reflection. Okay. 100 reflection is a short phrase which is condensing this long sentence that waves reflected from two successive planes which are spaced by an spacing a have a path difference of lambda, 1 lambda, right. If that is so, and if it was simple cubic, then I will get 100 reflection, everything constructive. But if it is body centered cubic, then there is a central atom. Okay. And just because in my drawing I have not drawn a blue arrow to the central atom, in actual X-ray experiment this will not happen. X-ray beam will travel and this central atom will also see. And if I am demanding that the path difference between top and bottom ray is lambda, what will be the path difference between this middle ray and one of these blue lines? Lambda by 2, simple geometry. And lambda by 2 is a constructive interference or destructive interference? Destructive. So, 100 will be killed. That is why there is no reflection in 100 reflection absent. We will do it little bit more mathematically by structure factor, but this is an intuitive way of seeing why 100 is absent in BCC. Okay. 100 is absent. Does that mean that I will never get reflection in this direction? Now, if I want to get reflection from these planes, from these horizontal planes of atoms, what should I do? How much path difference I should make? So, between the blue and red, if between blue and red the path difference is lambda, then everything is again constructive. But if blue and red the path difference is lambda, then what will be the path difference between blue and blue? 2 lambda. So, that means from 100 plane, now the path difference is 2 lambda. 2 lambda equal to 20. Okay. So, second order reflection from 100, first order 100 reflection absent means first order reflection from 100 plane is not there, but second order is there. So, second order reflection from 100 plane is there, but we have decided that we will never use second order. So, we will take this 2 to this side, right. No, I am making one mistake. This theta and this theta will not be the same. So, this is the second order. This is theta for the second order reflection. So, I am putting as a superscript 2, not a square, or maybe I should put prime. So, for second order I can write like this, but d100 by 2 we have shown is d200. So, everything is fine. If the path difference between this and this is lambda, then path difference between this and this is 2 lambda. So, it is a second order reflection from 100, but I will call that we agree by convention that let us call this first order from 200. When you will actually make some table or something in some tutorial, then that becomes clear that why Mrs. question, a student's question comes, why all this caboodle and this thing. But if you want to do things systematically, this is much more systematic than this, because here now you have to worry only about the planes. So, you can make a list of planes 100, 200, 300. Here you will have to make a list of plane as well as order 100, first order, second order, third order, 110, first order, second order, third order, fourth order, fifth order. So, doing things systematically becomes more complicated, because you have two variables here, the plane and the order. Here by systematically fixing the order 1, you have only one variable, the plane. So, in general you know that if H plus K plus L is odd, BCC will never show any reflection. Geometrically, whenever H plus K plus L is odd, there will always be this dal bhat mein musalchan. There will always be a middle atom. That is a geometrical result. If H plus K plus L is odd, there will always be a middle plane in BCC. So, you will not get a reflection. So, this is what, if you systematize that and study for different crystal structures, these are called extinction rule or systematic absences. Here is reverse of systematic absences. Either you can write the absences, but we are more interested in what is present. So, negative of systematic absences is allowed reflection. So, you will find that in simple cubic everything is allowed. BCC H plus K plus L only even, because odd 100 was not allowed, but H plus K plus L even 110 will be allowed, 111 will not be allowed again. FCC HKL all odd, all even. Diamond cubic some more complicated rule. So, essentially what we have done till now is to look at the peak position. Bragg's law as given is relating to peak position, theta is the peak position. So, Bragg's law as such can give only the lattice, but we want the entire crystal structure. So, we have to look at the peak intensities as well. Now, intensity has lots of factors. This list is very daunting: scattering by an electron, scattering by an atom, scattering by a unit cell, polarization factor, multiplicity factor, Lorentz factor, absorption factor, temperature factor. But it is thanks to one very famous author in X-ray diffraction field. So, any of you who have to ever touch any X-ray machine or write any X-ray examination should start, the starting point always is BD Quality Elements of X-ray Diffraction. It is an excellent text, very old now. The second edition is also 1978. Okay. Probably not available, I do not know whether available or not available, but most good libraries will have, and some of the older generation people may have their personal copies. So, you should look at this book definitely. And what I am going to do now from now onwards is actually following his chapter 4. This list is from his chapter 4, and the presentation also will follow what BD Quality has done in his text, taking many of his equations and many of his figures. So, first of all, the atom is scattering, as we saw. Even before atom, the electron is scattering. So, the scattering phenomenon begins with electron in the atom. So, X-ray comes and hits an electron in the atom, and that electron again, just like the atom as a whole, electron individually also scatters not in a particular diffracted beam direction, but in all possible directions. This was studied by the discoverer of electrons, J. Thomson. So, if you consider any particular diffracted beam OP, So, this is the direction of the transmitted beam, this is a diffracted beam, and again using the X-ray, that Bragg's angle nomenclature, we will call the angle between the transmitted beam and the diffracted beam as 2 theta, or the scattered beam you can say here. Now, J. Thomson, which was the discoverer of the electron, gave us this formula, which is Coulombi's chapter 4 equation 2, to write the intensity at P, in terms of incoming intensity I naught. R is the distance OP, and you can quickly see that R square is coming in the denominator, which means intensity is falling as R square. All of us know intensity falls as R square. So, further if P is twice more distance from here, the intensity will be 1/4. So, that is what that R square is doing, but the other term, this trigonometric term 1 plus cos square 2 theta by 2 is doing what will be the variation of intensity as you change this angle 2 theta. So, although an electron, single electron is scattering in all possible directions, the scattered intensity is not the same in all directions. So, scattered intensity is not forming a spherical symmetry, it is different in different directions, and that is coming in the scattered angle 2 theta formula there. So, this particular, the derivation involves, we are not deriving it. I think even Coulomb has not derived it, because you require more electromagnetic wave and Maxwell's equations to probably get to that. So, we are taking this equation, but what is interesting in this equation is that intensity of the diffracted beam from an electron varies as a function of 2 theta, because we are plotting I versus 2 theta. So, one contribution directly will be coming from the electron. That electron itself is not diffracting intensity equally in all directions. So, there will be intensity versus 2 theta due to the electron, and that factor is called polarization factor. But in this derivation, it was assumed that the incoming beam is unpolarized. So, again there is a misnomer. So, in some sense it should have been an unpolarization factor, because this factor comes by assuming that the incoming X-ray radiation is unpolarized. Cambridge University Physics Museum, the original gas discharge tube where J. Thomson discovered his electrons and worked out those formula. Such a simple experiment. Now, this is another father son pair getting a Nobel Prize, but this time much more interesting. Father got the Nobel Prize, J. Thomson got the Nobel Prize for discovering electrons. So, he showed electrons are new kind of particles. G. P. Thomson, his son, in 1937 got the Nobel Prize for showing electron diffraction, which is also part of this course. Later on you are going to study. So, father got Nobel Prize by showing electrons are particles, son got the Nobel Prize for showing electrons are waves. दोनों को अलग अलग. This was more intelligent. Rather than sharing a single Nobel Prize, they got 2 different Nobel Prize by contradicting each other. If you plot this one, how this variation takes place. So, if you plot 1 plus cos square 2 theta by 2, which was the polarization factor, then you will find that at 2 theta is equal to 90 degree, it is minimum, at 0 and 180 degree it is maximum equal to 1. So, the maximum value is 1, minimum value is 0.5. So, a factor of 2 difference in intensity of different diffracted beams can come simply because electrons scatter at different angles differently. Now, when you look at atoms, in atom you do not have one electron, but several electrons. So, this picture, which is again Coulombi's figure 4-5, if you take X-rays coming directly to different electrons, and going in the forward direction, you can show that in forward direction there will be no path difference, because this A electron travelled this much distance, the B electron also from incoming to the final is travelling the same distance. So, there is no path difference between these two beams, whereas in a non-forward direction, if you see, then there will be a path difference, because beyond this BD line they are travelling the same distance. Before the AC line they are travelling the same distance, but between AC and BD the top beam travels AD and the bottom beam travels CB, which are not the same. So, there is a difference in the path between these two beams going in different directions. So, because of the electron's position inside the atom, again a direction dependence of phase is coming, that in the straight through beam all beams will be in phase. So, you will get a strong diffraction, whereas in any other direction they will be out of phase depending on this 2 theta. Again the actual formula is not given here, but a calculation for copper is shown, that if you take a copper atom, single copper atom, then what is defined as F, the atomic scattering factor, varies from 29, which is the atomic number, down to low value of copper. The atomic scattering factor itself is defined here, that is amplitude of the wave scattered by an atom, amplitude of the wave scattered by one electron. So, you can see that at 0 it should be equal to the atomic number, because all the electrons are in phase. So, amplitude of the wave scattered by an atom will be 29 times, because 29 electrons are in phase compared to 1 electron. So, at 0 you will always have an atomic scattering factor which is equal to the atomic number of the atom, and beyond that it decreases, which has to be calculated from more advanced physics. But we are looking at that curve and the tables are available for use. So, when we have, so this is interesting, when we have different diffracted beams, I versus theta, I versus 2 theta plot. So, as 2 theta is changing, although same atom is scattering, but same atom is scattering at different power. Close to 0 it is scattering at high power, and as you go further in high value of theta, it is scattering at lower and lower power. So, there will be intensity variation, intensity decrease at higher theta values because of this. We now come, ये कब तक चलना है? 1 तक, ठीक ठीक. Now, we did something. We said that 100 reflection is not there in BCC, which means, but we satisfied the Bragg's law. For 100 reflection, this is the Bragg's law, and we calculated a value of theta. We can calculate theta from this. Theta is sin inverse lambda by 2a. But at that theta, when we go and set our detector, we do not see any beam. So, beam is not there, not because Bragg's law is not satisfied, Bragg's law is satisfied. Beam is not there because intensity is not there. This thing is sometimes said that Bragg's law is a necessary condition for diffracted beam, not sufficient. Example is 100. If I use this theta is exactly satisfying Bragg's law for 100 reflection, but for BCC 100 reflection we are saying is not there, intensity is not there, Bragg's law is satisfied. So, peak is not there. So, Bragg's law satisfaction is necessary, but not sufficient. The sufficient condition should come that there should be non-zero intensity. Whether the intensity is non-zero or not, mainly depends on a factor of how atoms are distributed in the unit cell motif, how atoms are distributed in the unit cell. So, when you consider the scattering, so look at that the systematic progress we are making. We first looked at scattering by an electron, then that was a Thomson's equation, then we looked at scattering by an atom, which was the atomic scattering factor. Now, we are adding all atoms inside a unit cell, all atoms inside a unit cell. So, the result of that is that if you add the phase difference, so essentially suppose this is some sort of unit cell where lattice along with motif is also there and different kinds of atoms at different location is there in this unit cell. Some compound crystal ABC, ABCD compound, 4 element. So, different atoms will have different scattering factor. There will be an incoming X-ray. So, atomic scattering factor will be different. An incoming X-ray will shine on all of them, and this one has atomic scattering factor F1, F2, F3, F4, all of them are having different atomic scattering factor, and then in certain direction which is reflected from HKL plane, we are seeing what is the net relation of these beams. Are they adding or subtracting or what? That will depend upon the phases, you know that, because when you are adding waves, it is the phase difference which matters. So, one needs to calculate the phase difference. Now, this is not very difficult, but one has to use, even Kuleti has not been able to derive it successfully. He does it for one dimension and then jumps to this formula. So, the correct way of deriving this is the reciprocal lattice method, which fortunately is not my subject, is Ashish Garg's subject. So, ask him the derivation for this. So, once he does reciprocal lattice, the concept of reciprocal lattice can be very easily used to show that the phase difference from the kth atom here, 4 atoms are there in the unit cell. So, phase difference from the kth atom in the unit cell is simply 2 pi times HKL. HKL is the indices, the plane from which the waves are getting reflected. So, HKL and UK, VK and WK are the position, the fractional position of this atom in the unit cell. So, U2, V2 and W2. Let me write X2, Y2 and Z2. X2, Y2, Z2 is the coordinate of atom in this position, and if I divide X2 by the A parameter, that is what is called the fractional coordinate U2. So, U2 is X2 by A2, V2 is Y2 by B and W2 is Z2 by C. So, those are UK, VK and WK. An amplitude of this wave. So, this is the phase. A wave is characterized by both the phase and amplitude. What is the amplitude? Amplitude we have already defined that it is a scattering from a given atom. So, it should be equal to the atomic scattering factor of that atom, which we defined in the previous slide. So, in the complex exponential notation, you denote this scattered wave from kth atom as AK, which is its amplitude, times e to the power I phi k, where phi k is the phase difference, and I is the imaginary number. So, this is the standard way of writing the complex form of the waves. All you have to then do is to add, if I have 4 atoms in the unit cell, add these 4 terms a 1 e to the power I phi 1, a 2 e to the power I phi 2, so on. And A's are of course the atomic scattering factor. There is a mistake here, this should be f k, and k is running from 1 to n. So, you will get an added up wave, and that is what is called the atomic scatter structure factor. F n is called the atomic scattering factor, f is called the structure factor. And this way of adding waves just gives you the amplitude. So, this is the complex amplitude of the wave. The intensity is a square of the amplitude, or in the case of complex amplitude, it is the amplitude multiplied by its complex conjugate. If all this is looking little abstract, let us do one exercise and then it will become clear that what is really involved. This you can do very nicely yourself, although it is shown on the slide here, but you really need not look at the slide. Let me switch off the slide. Yeah. So, let us do it for BCC. How many, now for first you have to decide in doing this that how many atoms BCC has. Two atoms. So, although 8 atoms at the corner, but 1/8 of 8 is effectively 1 atom. So, for the entire 8 atoms, I will select one representative which will be for my structure factor. So, the best one to select is at the origin, but these atoms are also scattering and I am leaving them. What will happen? Nothing will happen. They are also origin of some other unit cell. So, when I will move to the next unit cell, this guy who was feeling left out now will be a very happy origin for the next unit cell. So, similarly, all corner atoms will be origin of different unit cells. So, we are not leaving out anything, we are just limiting our calculation to one unit cell, then we can add up all the unit cells separately. So, in one unit cell I take out of these 8 corners only one, and that one, the simplest one is to choose at the origin. So, I get 0 0 0. Then if it is a body center, the second atom is the body centered atom, which is a by 2, a by 2, a by 2, the coordinates a by 2, a by 2, a by 2, x y z coordinate. So, u v w coordinates, the fractional coordinates will be a by 2 by a. So, half a by 2 by a, half half. So, I have just 2 atoms. So, in this summation you have only 2 terms, one at 0 0 0 and one at half, and if it is a cesium chloride structure, then the atomic scattering factor will be F cesium, F chlorine. If it is a normal BCC, then the atomic scattering factor is also same, F and F. So, for a normal BCC you calculate, थोड़ा tutorial करा देते हैं. So, just add 2 terms, everything is there. अपने pencil से करोगे तो याद रहेगा. 100 reflection is not there in BCC. We are now getting more systematically through this structure factor calculation. So, that is the calculation I was asking you to do. So, all we have to do is to add up from 1 to n, but BCC is a simple structure, only 2 atoms. So, only 2 terms F E 2 pi I H 0 K 0 L 0 for the atom at the origin, and H half K half L half for the atom at half half half. So, when you write this, f is equal to 1 plus e to the power pi I h plus k plus L. Now, you can see that the systematic absence rule which we wrote is coming out from this structure factor. We have now the proof of that statement. Previously, it was just a statement that if h plus k plus L is even, then you have e to the power even pi I. E to the power even pi I is always equal to 1. So, f becomes 2f, and e to the power odd pi I is always equal to 0, and f is equal to 0. So, however, now your structure may be more complicated and there will be more and more atoms in the unit cell, but all you have to do is, for example, diamond cubic, how many atoms in the unit cell? No, that is for FCC. FCC is 4. So, FCC when you will do, you will add 4 terms. Diamond cubic if when you will do, you will add 8 terms. But the procedure is exactly the same, and it is not big mystery, and the physics or the intuition behind that I had already shown you by the pictures, that when it is saying h plus k plus L is odd, here it is coming straight from high power mathematics, that the intensity should be 0. But I had shown you, at least one mental picture one should keep, that when h plus k plus L is odd, actually there is a middle atom in the crystal which we have not accounted for, and when we will account for that, that will be half wavelength out, and that is what is making this 0. So, this is also actually systematically adding all the phase differences, amplitudes and phase difference. So, this is the vector addition of all the phasors corresponding to waves scattered by just 1 or 2 factors maybe before we break for lunch. Multiplicity factor is very, very simple and very interesting. When you write 100 family, okay, then it is either 100 plane or 010 plane or 001 plane. Come to the formula here. Formula is symmetric with respect to h, k and L. So, D100 will exactly be same as D010 will be exactly same as D001. So, when I will apply to the Bragg's law, lambda is equal to 2D sin theta, theta will come exactly the same whether it is 100 or 010 or 001. In other words, all these 6 planes will be diffracting in the same theta direction. So, there are 6 members who are ready to support the 110 that direction. But when you come to 111, there are 8 members which are supporting that direction, theta corresponding to 111. That is multiplicity. This is called the multiplicity of the plane. We are saying multiplicity of 100 plane is 6, means in the 100 family there are 6 equivalent planes. Multiplicity of 111 plane is 8. In the 111 plane family, there are 8 equivalent planes. So, obviously, if there are 8 planes which are diffracting and there are 6 planes which are diffracting, if everything else was the same, everything else is not the same, because you know that the 111 theta will be different from 100 theta. So, the structure, remember the polarization factor, that itself will give you different intensities for these. But for the moment, if all other things are equal, still there will be a difference because of this factor, that there are 6 members in the family, there are 8 members in the family. So, 111 will be a stronger beam than 100 beam, and the strength will be 6:8 or 3:4. So, 100 intensity will be only 3/4, 75% of the 111 if other things were equal. This is what is called the multiplicity factor. Polarization factor we have already seen. This is coming straight from atomic electron scattering and the fact that the incident wave is unpolarized. There is two other factors which are trigonometric in nature. okay, and time is not there, but quality is there. So, do not worry, you can always go and read it. I have also read from there and telling you. So, the integrated intensity of the peak can be shown to be 1 by sin 2 theta, depending on 1 by sin 2 theta, that as the higher angle peaks will be of lower integrated intensity by this factor. Then this is looks dirty, but is actually simple, that how many different crystals are oriented properly for different direction. This is very interesting. All crystals do not diffract for any given peak. Remember, we are doing powder diffraction. Powder means sample is polycrystalline. And each sample, the planes are oriented differently. And suppose we are talking of 1-1-1 diffraction. So, which means 1-1-1 plane should be reflecting, but my diffractometer geometry is such that when the incident beam is making at an angle theta here, the detector will be also at an angle theta from the surface. So, from Bragg's law, I will get a 1-1-1 reflection only if 1-1-1 plane are in the mirror reflection orientation. So, let us say for this grain it is mirror reflection orientation. So, this grain will reflect, but this is a polycrystal and all grains are differently oriented. Neighboring grain, the 1-1-1 plane is like this, does not contribute. It will contribute to this area. The X-ray will come here and will not contribute anything, because it is not in the diffraction orientation. This again does not contribute, does not contribute. This one, it is again parallel to this, will contribute. So, for any diffraction beam, only a fraction of the crystal contribute, and for different beams different crystals will contribute. So, the intensity will also depend on that for any given direction what is the fraction of crystals which are properly oriented for that diffraction or reflection. And that turns out, surprisingly, from this analysis, surprisingly it turns out that the fraction of properly oriented crystal itself depends on theta. So, with respect to the integrated intensity, this derivation is very simple, but I do not want to read it out now. Okay. And this diagram also looking complicated, but it is actually simple. So, during lunch time, if you want to really understand, I can tell you one to one, but currently as the lunch time has just arrived, I do not want to get into that. But essentially the physics I have explained to you. Essentially we are trying to calculate what fraction of grains are oriented properly for any given theta, and that becomes a function of theta. So, the integrated intensity will also be a function of same theta. So, that gives you a cos theta. Each diffracted beam, here we were showing a diffracted beam, but actually in powder diffraction you have a diffracted cone, because grains can make this angle 2 theta anywhere about this axis. So, wherever this 2 theta is satisfied, you will get a diffracted beam, but 2 theta you can rotate about the transmitted beam. So, you will get a cone of 2 theta. So, intensity is distributed over that cone, but your detector is moving in a circle. Your detector is moving in a circle. So, detector is moving, and if that is the width of the detector, if this is the width of the detector, detector is not looking at the whole cone, is only this part of the cone, this part of the cone, this part of the cone. So, if it is a smaller cone, detector captures a large part of the cone, whereas if it is a larger cone, detector captures only a small fraction of the cone. Okay. So, that is the meaning of fraction of diffraction cone recorded by the detector, and this can again by this simple geometry can be shown that will be 1 by sin 2 theta. So, all that then you have to do is to put all means if we put all the trigonometric factors together. So, due to reflection at non-Bragg angle 1 by sin 2 theta, fraction of properly oriented crystal cos theta, fraction of diffraction cone recorded 1 by sin 2 theta, that is what is called the Lorentz factor, all of them put together and simplified trigonometrically cos theta by sin square 2 theta. But apart from this Lorentz factor, we already have a polarization factor which is also trigonometric. So, sometimes both these trigonometric factors are combined into a single polar factor which is called Lorentz polarization factor. So, if you have not followed the derivation and all, finally, for application it is very simple that each peak will have an intensity multiplied by this term. So, if this term is high, the intensity is going to be high, and if this term is low, the intensity is going to be low. Apart from the structure factor, if a structure factor is making the intensity 0, then this will not help, but given that a structure factor is giving you some intensity, further this will be multiplied to give you the. So, and this factor itself if you plot as Bragg angle, shows an interesting variation. So, at lower and higher angles of theta, it is high value, at around theta is equal to 45, it is very low. I think I can leave the absorption and temperature factor. No, temperature factor has an interesting history, and as you have already realized that I like history. So, maybe I can share this. And because this was a big question. So, I will end with this. In the Lave's proposal, I told you Lave said if crystals are periodic arrangement of atom and if X-rays are wave, then I will get the diffraction, and he was talking about this in some coffee house in Munich with his colleagues and all. तो बेकार की बातें कर रहे हो, कुछ नहीं आता तुम्हें. टेम्परेचर का सोचा? अरे भैया पीरियोडिक है या नॉन पीरियोडिक है, देयर इज थर्मल वाइब्रेशन. तो वो तुम्हारे लैटिस पॉइंट पर एटम बैठा हुआ थोड़ी वेट कर रहा है एक्सरे को तुमको पीरियोडिकली डिफ्रैक्ट करने के लिए, और ये कोहेरेंट वेवलेंथ ये सब ऐड सब्ट्रैक्ट कर रहे हो, वो तो वाइब्रेट कर रहा है, और वाइब्रेशन भी रैंडम है, एक डायरेक्शन में नहीं वाइब्रेट करे. तो लैटिस रहा कहाँ? वेयर इज द लैटिस? By the logic, by their strong logic of thermal vibration, they wanted to throw cold water on Lave's hope. और अगर कमज़ोर दिल का आदमी होता, अरे यार ऐसी बेवकूफ़ी कर दिया, मैं अभी सोचा नहीं टेम्परेचर के बारे में, अब क्या एक्सपेरिमेंट करना, छोड़ दो, एक अच्छा आइडिया था लेकिन ख़राब हो गया. So, don't believe theorists when you are also doing experiments, and don't believe all this sort of logical arguments, because logical argument is also product of human brain, and human brain is not ideal, human beings are not ideal. So, a non-ideal brain applying an ideal logic will not give you always ideal result. Okay. So, whatever the law, and nature can behave in a different way. So, see, nothing was wrong in this logic, very logical. Atoms are continuously vibrating with random amplitude, thus there cannot be any periodicity of instantaneous position. Instantaneously crystal कहाँ पर है? एक atom वहाँ भागा हुआ है, एक atom यहाँ भागा हुआ है, you are saying all at distance A. Where is the distance A? Where is A, B, C, alpha, beta, gamma? Nothing is there. So, there cannot be any periodicity of instantaneous position, and therefore, there will be no sharp diffraction pattern. But nature decided differently, X-ray decided differently. Somehow X-ray is despite all the random vibration, X-ray is able to see the mean position. And it's the mean position which it is telling you that it is FCC. It is not telling you that instantaneous position. Instantaneous position cannot be FCC, but it is vibrating about a mean position, an atom with which in our analysis nowhere came. अभी तक तो हम झूठ बोल रहे थे. That's why I thought that this temperature factor slide is important, because it bunks or junks all our previous discussion since morning that we have a nice periodic arrangement of the lattice. कहाँ भैया क्या बात कर रहे हो, सब कुछ वाइब्रेट कर रहा है, सब कुछ भूल जाओ. तो अगर अभी तक भूल गए तो कुछ गलत नहीं किया, गलत बातें भूले हो. सही बात यह है कि there is vibration and there is no lattice. But Lave went ahead, did the experiment. Interestingly, and this is from Kettle's Solid State Physics, very famous book. So, it turned out, after doing the experiment, it turned out that of course, thermal vibration lattice parameter will increase, so peak will shift, lambda is equal to 2d sin theta, d is larger, lambda is same, so theta will be lower, peak will be shift to lower theta. That is one effect of temperature. Intensity of the diffraction lines decreased, intensity of the background scattering increased, and rather surprisingly there was no peak broadening. One thinking was also that so much vibration is there and random vibration, even if peak is there, it will broaden so much that it will merge with the background. None of those things happened. And so, handling these things, effect of temperature is there, but it does not kill the diffraction pattern. It only modifies the diffraction pattern intensity and the background intensity. It decreases the peak intensity, increases the background intensity. So, taking into account the effect of temperature on the peak is what is called the temperature factor. So, here all the factors taken together, बस अब खाने के लिए चले रहे हैं. All the temperature, this is the last slide I think. All the factors taken together, this was the structure factor. Remember, structure factor squared will give you the intensity. This is the multiplicity factor. This is the Lorentz polarization factor, and e to the power minus 2m in the end is doing the temperature factor, which we have not derived or not talked in detail anything, but you can look up Coolity. Coolity also has not gone into much detail about this. So, if you really want to look up temperature factor in detail, the Debye-Waller factor and all, you will have to go to more advanced books. So, this will be the final intensity expression. And so, thank you very much.